Alright, welcome everybody. This is going to be the life of a pixel. I've given this talk a few times. This is the TriLUG version. It's iterated a few times over the years. I'm a professional computer nerd, and so who am I? I'm a University of Wisconsin graduate, born and raised in Wisconsin. My wife started her PhD here at NC State last year, dragged me down south. We've enjoyed Raleigh. I ended up finding with the TriLUG group. It's been awesome. And yeah, so I have a history working in Linux Android graphics for about 9 years now. So I like to pretend I know what I'm at the level where I think I know a lot. So give me another 5 years. I work for a company called LunarG. They're based in Colorado. They're a 25-ish person consulting company, I guess, because we specialize in 3D graphics software. The best way to explain it is people are probably aware that most of the world software ecosystem relies on very small tools that just hopefully work. So we kind of specialize in this niche, but with 3D graphics. So we get a bunch of the companies who just need things to work, especially around 3D graphics tooling, to just pay us to do it. I've been fortunate for the last, 3 years now that Valve has been gracious to fund the thing I work on. And so we work, so they just, they're not the only person that pays for our company, but they're one of the main ones. So what you guys are about to witness is pretty crazy. It's going to be quite a dense talk. It's going to be 3 parts. First part is going to be about, why do we have a GPU? How do we get here? How do you program one? And then, I'm going to explain the entire Linux graphics stack. It's going to be epic. And there's going to be so much information. I'll sit here all night and talk about it. So if you didn't see something, and I'll post the slides later. So I'm going to shoot through these really fast.
And we have the recording.
Yeah. So GPU. Hopefully you guys know what a GPU is. If you don't, it stands for a graphics processing unit. So it's a separate piece of hardware to do graphics processing. You can use your CPU, but it's slow. So how did we get here? Well, imagine if you're back in 1990 and your boss came up to you and said, "Hey, get this cube and move it over here." You'd be like, "Okay." And there's no Gemini, no ChatGPT, but you go to your desk and you figure out, okay, let's take a look at this cube. There's 8 vertices on this cube. Okay, I just got to move it over to the other side of the screen. Or here. Luckily, you took a linear algebra class and you learned that if you take a 3D point in space, multiply it by some matrix, mathematically, you can move it anywhere. Okay, cool. So you do that with one of the vertices and the next vertice, and yeah, you just kind of slowly get through, but this is kind of slow and painful. So here's something that people realize. The order does not matter. You can move these vertices in any order you want. That's the key here. So it doesn't matter which one goes, as long as at the end, they all get moved. This independence allowed people to decide, okay, let's do this all at once. That was pretty fast. Let's try it again. Ready? See how fast that is? It's way faster. So the whole point of the GPU was to move a vertice. And then over time, we decided to add lots of vertices. And then when you want to play a game, you play at 60 FPS. That means you have 16 milliseconds. These are tight budgets right here. And if you're on a 10K monitor, that's 2 million pixels. But we're in 2025. We're in 4K world now. So you have 8 million pixels. Think about it, 8 million pixels. You have 16 milliseconds to fill that whole screen. So this is where you need a dedicated piece of hardware for. You got VR, 2 screens. You got AR, you're 16 milliseconds, now you lose 4 of it to the camera latency. So again, these are very tight constraints. So a lot of you might know that CPUs are really good at doing one thing, and a lot of you probably already know this because GPUs are now cool, that GPUs are parallel, do all the things at once. So the kind of moral of the story is GPUs are designed for parallel. And I know some of you guys are thinking right now, oh yeah, I've done POSIX P threads. This is different, okay? Threading is different than parallel. Threading concurrently is like my USB. Like my CPU is able to use my USB while also getting Wi-Fi and the keyboard. That's concurrent threading programming. That's what P-threads are for. Parallel is you're doing the same operation across a bunch of data points. Kind of like that cube, moving that cube. So the classic kind of like hello world for this is, let's take 2 arrays here. So I have 2 arrays filled with some random piece of data, and we're just going to add them together. So A plus B equals C. And with this, it's a very simple operation. We'll start from the left. 4 plus 1, 5. 2 plus 5, 3, 5. And you just kind of go work your way over, right? So that's how you add two things in an array. So in a CPU, if you look at this code, it's just a for loop, and we're just going to do A plus B and put in C, right? Well, what happens when n is 10 billion? okay? So these are just rough numbers, just to give you the ballpark idea. If you have a CPU at 3 gigahertz and it's on one thread, that's 3 seconds. And you can't even use the CPU for the rest of your machine. But you put it off to a dedicated piece of hardware, even though it's a little bit slower, because of the mass sheer parallelness, you can get this down, to milliseconds. So I know what you're thinking. Damn, these things are fast. And now you're like me, my old self. I thought, man, we should GPU all of things. This is awesome. Like, the first time I heard this, I thought, wow, everybody's missing out on this. So I'm going to hold you right there. So I show you some things that you can't use a GPU for. Let's look at this example. So you'll see this. I have A plus B, but I put it to A of I plus 1. So I'm moving it over 1. So let's do this again. Okay? So now I have the A plus B, but it's going back into A. So when I add that to 5, I have to go around and add it back to the source. Same thing. I had to take 8, but I got to add it back to the source, and so on. Well, remember what I said before. Order does not matter in a GPU. You can go in any order that's independent. That's what the whole point of the GPU. So imagine in another world, a different scenario, we go the other way. Let's go right to left this time. So now we add it, and we go do the same thing. And what happens at the end? We have different values. Right? You see that by going a different way with different values? Congratulations, everybody. You hit your first race condition. So if you don't know what a race condition is, this is the whole idea of, if you run this thing 10,000 times, depending on what order it picked, it's going to be a different value. And this is not good if you're doing a banking transaction and one thing's doing a withdrawal, one thing's doing a deposit. You really hope you know what order that's happening on. So this is where, race conditions are a big concern on the GPU. So yeah, you don't mess with race conditions, okay? It's just a bad late night. Also, memory is slow. Like, I can't empathize how slow memory is comparatively to computation. So a classic example, this is, again, just some arbitrary numbers. Let's say your CPU is super slow and takes a second to compute. And your GPU is instant. Well, the time it takes to transfer that data from the CPU to the GPU and back might just be even slower or the same amount of time. So what this ends up doing is it eliminates you, offloading very small tasks. That's why you just can't take a small little function and throw it over to your GPU. The time it took to bring it to it and back, you worry would have been faster if you just did it on the CPU. So that's why small workloads don't do well. And so the kind of rule of thumb we have is if you can't feed your GPU, don't use it. So yeah, I will give the credit to Device Hector, who created this image of GPU eating candy and spitting out rainbows. So what we learned so far is GPUs are great for 3D graphics, not great for everything, and I realize I talk like a 1.25 speed YouTube video. That's how I am. I'm sorry. The recording, just put it to 0.75, it corrects itself. We're going to keep moving on though. So everybody should know GPUs are cool now, right? Yeah. I started this when I started back here. Now, I didn't put my money in NVIDIA, but I started using GPUs back there, where I had to explain to people what GPUs are. Now I just tell my mom's friends, you know that NVIDIA company? They're like, oh, yeah, I've heard of that. So how did GPUs become cool? Let's say I give you $100,000, and I say, build the best PC possible, because you want a game. Okay. Well, here's the problem with multiple GPUs when you're gaming. You have 2 GPUs, they each have their own memory. So you get the image ready for your Crysis 3 or whatever, you put in 1 8 gig of RAM. Well, the other GPU can't see that memory. And remember I said memory was slow? That's the bottleneck. And so there was things like SLI and Crossfire. It's a pain to develop, it just wasn't worth it, and eventually the kind of industry abandoned this. So that's why when you game, you get 1 GPU, and then the rest of the money you spend on everything else, okay? Well, let's say now, change the question, give you $100,000, but you can use the GPUs, and you gotta build the PC for training AI. Whoa. So, ChatGPT-4, that's like a 2 trillion parameter, and this thing runs offline. People are expecting this to take hours to run, not 16 milliseconds. Also, when people program these AI stuff, it's designed already to be broken up. It's not like a game where they expect it to be on 1 GPU. They never expect an AI to run on 1 GPU. So these things are designed from the ground up to be parallel, and so the more GPUs, the faster you can train. So if you're OpenAI, your shopping cart is just as many GPUs as you are allowed. And so this is where you can sell an AI company 100 GPUs, but you can only sell the gamer 1 GPU. So, okay, hopefully at this point I've convinced you. But like, how do you use the GPU? Okay, I've hopefully made everybody want to use the GPU, but how do you do it? So hopefully most of you are aware of that you have this the band something architecture. Someone tell me.
Van Neumann.
That's it, him. CPU, RAM, hard drive. You roll your program off the hard drive, put in your RAM, and then the CPU can work from it there. So now you have this new component, the GPU. So how do you communicate with it? Graphics APIs. Guys, the answer is graphics APIs. So how a graphics API works? It's really simple. The CPU gives off data and just kind of like instructs the GPU what to do. Cool. So let's say you have the CPU, you have some memory, some buffer of data, you throw it over to the GPU. You have the shader kernel, you throw it over to the GPU, and the CPU says, run it. Okay, this is gonna be really tangential, but trust me on this one. Someone give me a company that makes routers.
Cisco.
Cool. These companies make routers, right? Cool. Do these companies make routers? No, but they talk to routers. These are different companies though, right? Google, Apple. Right? They don't make routers, but how do they all work together, this whole ecosystem? They use what's called a standard. Wi-Fi, by all means, is by the amount of adoption. It's a pretty successful standard. Everybody just seems to have Wi-Fi working. Awesome. Let's try this again. Who makes GPUs? These companies make GPUs. Who make things that use GPUs? These products. How do they talk together? Guys, it's graphics APIs. I'm telling you, the graphics API is how you do this. So, OpenGL is a classical graphics API, and the whole idea is you write to it once, and it will work on everybody's hardware. You know, big asterisk there, but it works on everybody's hardware. So OpenGL is kind of the OG around here. It's 33 years old. It's older than most people, some of the people in this room. OpenGL, yes, was the embedded version that they put on like mobile devices. Well, in 2016, the ecosystem came and said, we need something better than this. GPUs have grown a long way. They went from being a dedicated, move this vertice over there piece of hardware to now doing AI training, all this stuff. We needed more control of our GPU. So in 2016, the world explicit APIs came out. Vulkan is, as you can tell by my shirt, I'm very biased. Vulkan's the new, better one. It's OpenGL. It's from the same Kronos group that made OpenGL. They made Vulkan. They didn't want to call it OpenGL 5, so they called it Vulkan. It's kind of a better way to put it. It gives you more control of the GPU and it's very cross-platform. But some of you guys are in Tim Cook's land and you don't get to choose. You're on Apple, you use Metal, okay? That's your rules. You bought the MacBook, you're stuck to using Metal. Cool. And if you're on Microsoft, if you're on Windows, you can use DirectX 12. DirectX has been from 9, 10, 11 were very successful APIs. And then DirectX 12 is when they did the jump kind of like from GL to Vulkan. DirectX 11 to 12 is also that big, you know, let's make everything really explicit and control and all that. So these are your three options if you want to program a modern GPU and a modern API today. The big thing about Vulkan is it's very cross-platform, not just Linux, but Windows, and it even has you can even get it to work on Mac very well actually. And people put a lot of time and effort in that. So the Vulkan has a vast range of where it works. So you don't have, okay, don't feel ashamed. I'm not going to ask you to raise your hand, but I know at least one of you in here is a JavaScript developer. It's okay. I get it. It's okay. So luckily for you, there's WebGL and WebGPU. So these are, again, standards graphics APIs, but the browser has, they're done in the browser. And it's really cool because you can use your GPU via a web browser, which I think is cool. So the basic idea, all the browsers, they use a standard like web GPU, and then depending on your, they'll either tie down to Vulkan, DirectX, or Metal, talk to the GPU. Same thing, we have WebGL, which was the old one, talk to the OpenGL ES, same idea. So, this is how we have these, it's a lot of layering, okay, I can tell you that right now. So let's talk about some abstraction levels. So you have like your engines, you have your frameworks, you have the APIs, and you have, at the bottom, you have your explicit graphics APIs like Vulkan. I'm gonna take a moment to talk about these engines, because engines are amazing. Oh, really quick, I realize we're in Raleigh, so everybody knows about Epic Games, hopefully. So that's actually a cool thing. So, usually, I'm from Wisconsin, so Epic is a healthcare company, and so I've never told people they're like, the healthcare company? So anyway, speaking of engines, they're amazing. They're free, asterisks, applied, but you can just download it right now, which is pretty incredible. You can just go download it and start using it today for free. They come with lots of videos and tutorials, And now, like the rise of things like Godot, yeah, they're open source, and so you can just do whatever you want. These engines are amazing, and my unsolicited advice, if any of you are liking or want to become a game developer, I would strongly advise to use an engine. Don't put your ego aside. No, but actually, put it aside. Don't make your own engine. It's a learning. Just don't. Just use an engine. Make a product. It's great. Okay. But we didn't come here to talk about engines. We came to talk about graphics, right? Vulkan. Okay. At its pure graphics at its purest form. So, what is Vulkan? How do you use it? Well, Vulkan is a 5,000-page specification that all the GPU vendors that we gather once a week to all talk about how to build this API that we all somehow agree upon. These are like it only gets more and more complex the more you go into it. I've been doing it for years. I learn something about it every week. So yeah, this is gonna be very overwhelming. Trust me, I am a professional. And this next part, I'm already talking fast, but the whole point is, I'm not gonna teach you how to use Vulkan. Like, you can spend a weekend on it, but I'm gonna give you an idea, like if you're using Vulkan, what you're gonna see. So first thing I do is you gotta pick a GPU. If you're using Vulkan, you don't know, the classic example of this is you're on a nice machine, and instead of using your nice, fancy, dedicated graphics card, it uses the Intel integrated CPU graphics. So it's gotta, make sure you pick the right GPU, and then you gotta pick which surface to render on. Because you might have, you might just tell it to render to a surface. And then we have a thing called a swap chain. So you display an image, but you actually in the background, you have another copy ready to be rendered to. So you render to that image, and then ready, swap. You get the next image ready in the background, and when they're ready, you swap. That way you can because there's a latency to displaying on the screen. Let's say there's a millisecond to display on the screen. You can use, during that latency, you can get the next frame ready. And so that's kind of the whole idea of these swap chains. So let's allocate some memory. First thing, we need some image views. So the idea is that we have a lot of these 2D, you can imagine with a 2D screen, you have a lot of 2D array of images. You've got to allocate all of these. We can talk to 3D, we're not getting there right now. So GPUs actually don't even have the same way of viewing memory as a CPU. So the CPU, if you have 2D array, you think of it, you know how to access it. You ever probably done that with a basic C program, finding your pointer in a 2D array. GPUs don't do that. GPUs access things in quads because of historical reasons. And yeah, so the first thing you gotta do actually is get your memory from the C and the one on the left. That's how you normally think of a 2D array. The GPU, you don't know. It's implementation defined. So you gotta first copy it over. Fun fact, if you want to then print your thing to a JPEG, you gotta bring it back. So let's get a little example right now. I got a little graphical example right here. So to render this on the screen, first thing you need is geometry. Okay, so you gotta get the vertices, the XYZ coordinates, and we're gonna throw that into a vertex buffer. So the whole point of a vertex buffer is just holding all the vertices, all their data. Well, we're gonna want color, and we're gonna allocate memory for that. Okay, so now our vertex buffers get a little bigger. Put some color there, but okay. Now we need a normal. So when you want to shine light, if you take your physics class, light bounces depending on the normal. So now you got to find the perpendicular angle to a surface and have that value baked into your vertice. So we're gonna have to put that in our vertex buffer. We're starting to run in a room. Textures, more memory. So yeah, so now we have to have a texture position for a vertice, and a lot of times we have these things called, you can also have a thing called index buffer, which is just a buffer, another buffer that points to what vertice you want. The GPU world loves lookup tables, and I mean, it's an indirection on indirection and indirection. You'll find me just getting really mad debugging things. I realize I'm 3 pointers deep trying to figure out where we're pointing to. We love these. Another thing GPU programmers love is when you say instructions, you mean your assembly instructions. The fastest one is the one never ran. So we have a lot of tricks up our sleeves as graphics programmers. A classic one is the depth buffer. So I have 3 colored images here. And depending on which order I display them in, they're gonna be in different orders, right? If you want the blue in front or the yellow or red, you need to know which one's in the front and which one's in the back. So what you can do, same thing, so think about this. Think if you have a large scene, you have a really complex, object, but it's hidden. Well, just don't render it. You can't see it. So if you realize it's behind something, you don't have to like render it. And this is a classic graphics trade-off where we spend time building up this depth buffer so we can like discard a ton of time later. So this is like where a lot of graphics research is sometimes. It's just figuring out, this seems a little counterintuitive to spend time here, but if we do it, we'll save a lot of time down the road. So a depth buffer is just, you take one of those image views of your screen and you just put a value on it of every object, and you find the one that's the closest and you pick that one to render. So everything behind it is just excluded. So first thing, so now, as you imagine, you got to allocate more memory for that depth buffer. It's very easy to run out of graphics memory, if you can't imagine. So next thing is the thing called, I'm going to call it the magical graphical pipeline. If you take, has anybody here in the graphics programming course or taken a graphics programming course? Have you guys heard about the pipeline?
Oh yeah.
Yeah, it's the pipeline. Like, what is this pipeline? The best way to explain it is you're going to start at vertices and you're going to get down to an image, a rendered image. In the way there, you have a bunch of like knobs, things that you can turn on, like a depth buffer. You can turn on the depth buffer, you can turn it off. Like these are like all the knobs you can turn on and off as the vertices walk their way down the pipeline. So that's why they call it the pipeline. Okay, next thing we gotta do is we gotta build commands. We're gonna put them in a buffer. So we're gonna say, they're gonna build these commands up for your GPU like, hey, use this vertex buffer. Hey, use this pipeline settings. Draw. And they're gonna get the next one ready, right? But then in Vulkan, you can do this in multiple threads. So you can thread these. And you're just building up these instructions to send down to the GPU, which, yes, finally, GPU time. Let's send them down to the GPU. First thing you're gonna do when you send down to the GPU is you can run through the pipeline. And it's gonna get to a vertex shader. The vertex shader is gonna take all the things in the vertex buffer and find out where it is on the screen. Who here has heard of shaders before? Raise your hand if you've heard of shaders. Fools, you activated my trap card. I could give a college course on shaders. Half of my job is dealing with debugging these shaders, tools for these shaders. This is a deep rabbit hole. I'm gonna save you from it. But yes, these shaders, for the people who aren't aware, they're just they're the programs that execute, like instead of a C program, you run a shader and it executes on the GPU. Enough said. Oh, don't forget, we've got to allocate all the memory for the shaders as well, okay? Then, once you run through the vertex shader, you're going to do a thing called rasterization. And the whole point of rasterization is a fancy piece of hardware that's just going to figure out if this pixel is, because your GPU is an infinite precision. It's going to, your screen is not. Your screen is very discrete, how many pixels it has, and it's going to figure out if it fits in it or not, and it's going to color that in. And then you run through the fragment shader. This is where you do all the cool lighting effects, and now you have each pixel, and you can like do things like a blur effect by taking the pixels around it and averaging the colors. This is where you do more cool fancy logic. And so when you are done with the vertex shader, you go out to what's called like an attachment, and like this right here is a depth attachment. So the black is whatever closest to me, white's really far away. This is a velocity attachment where you're taking the last frame, you're detecting what was like, the motion, how much motion there was between the last frame. And then I'm not going to get into all this, but this is basically all the techniques to give your image like kind of life, essentially. And then you put them all together, and you get through a render pass, and you get a nice image. But then you got to do some post-processing, like adding the particle effects, the transparency, the lens flare, all that stuff. You can just kind of just constantly painting onto this image. And then, don't forget we gotta synchronize this. The CPU and GPU are two separate things you gotta synchronize. And like I said, you don't mess with race conditions. But after a few moments of doing this, you eventually come out with a rendered image. And yeah, that's kind of how Vulkan works, is you just gotta do all that. Cool. Yeah. Okay, so I'm 24 minutes in, I haven't talked about Linux yet. And we're gonna TriLUG medium. So I'm gonna talk Linux a little bit right here. So who's ever seen this image? The Linux graphics stack. This is from Wikipedia. Yeah. Okay, if you go to Wikipedia and you type in Linux graphics stack, you see this. This is very confusing and misleading in my opinion. So really quick, if you don't care about Linux, you're just here for graphics, cool. But this next stuff is not just for Linux. This is for all platforms. Mac, Windows, Android, Nintendo Switch. They all have their own ways to do like Windows system, like displaying things to the windows. They all suck. They're all awful. The only advantage of Linux is at least it's open source, but they're all bad, okay? So the biggest problem with this world is engineers love reusing terms. So graphics, this is the first word we love overusing. So there's 3D graphics. There's like, I make 2D graphics. I've told people I'm a graphics programmer and they assume I use Adobe Illustrator. So graphics is a very overused term. So we were just talking about Skier earlier. So this is on my Android device. You can go to developer settings and you can turn on showing the windows, and you can see on like a mobile device, it's just a bunch of boxes being rendered. So a lot of graphics is 2D graphics. Window, this is another overused term. There's the application, it's your monitor the window, it's the app the window, there's the entire, if you're on Windows and you include the Windows.h header file, everything's a window. Yeah. Next one is frame buffer. Has anybody heard of frame buffer? Yeah, everybody loves to use the term frame buffer. It's literally a buffer to hold your frame. It's a 2D array of pixels, that's all it is. But everything's a frame buffer, because we're always putting frame buffers in other frame buffers. Linux has this FB0, FBdev, which we'll get to more in a bit, but yeah, so that's what FB stands for, frame buffer. Okay, let's start from the bottom. When you're trying to build up graphics, what's the simplest thing? TTY. Does anybody use TTY? Yeah. If you haven't, it's a util that makes your computer look like it's a 1980 terminal. You can go right now on your laptop, a Linux laptop, you Control-Alt F2 through 8, and you'll get this screen. Yeah. Okay, so this is...
I was confused for a second because I thought everyone used the terminal emulator.
So this is as primitive as it gets for rendering on your computer right now. So how does this render pixels? How do we get this up to the screen? This is still putting pixels on the screen. So the fundamental idea is this program takes your inputs of letters. It's gonna, it takes the letter F and it's gonna figure out which pixels to draw in for F. And then it's gonna use the kernel driver to talk to the GPU. And then, this is the part I actually don't know too much about, because once you start talking with HDMI protocols and all that stuff, essentially you're gonna eventually pass it over to some HDMI, VGA, something, and then that screen's gonna notice that a new thing came in. Boom, you display some text on the screen. You can actually look at your frame buffer. There's a virtual size. So my laptop is a 1920 by 1200. So that's how it knows how big my screen is to render the pixels to it. And yeah, it's very simple. You just allocate this times the size of your, whatever you want to put per pixel, and you have your first frame buffer. Congratulations. So we get to the boot screen. Okay, cool, we're gonna log in. How is this rendering pixels? We're not even logged in yet. So this is what's called a display manager. It's kind of its one main job, which is to let you authenticate yourself and log in. It'll kick off everything. It's a special lockdown frame buffer. So yeah, and you obviously, because we're in Linux, there's more than one option you can have. Who's ever done this? Who's ever gone, when they open up, and gone down to the right and changed this? Yeah, okay. Welcome everybody, we got to windowing systems. Yay! There's two windowing systems everybody uses on Linux, Wayland and X11. Yeah. Who's ever tried to look up this, understand what Wayland X11 is? Anybody try to deal with this? Yeah, okay. So they work off this idea of client server. So I'm on my laptop. I want to everything is on the laptop, but the cool part about X11 Wayland as a protocol is I can remotely access this. I can bring input to this computer, because this computer can be running the server, and I can be sending inputs like a client. So that's why they build these as client server models. So in this case, the clients are the apps. Your Firefox, your File Explorer, your VLC, and the compositors are the servers. And depending on what flavor of Linux you have might have Mutter, you might have KDE, and then there's tons of these. So here is my laptop, my Pop! OS laptop, and I have VLC open. Okay? Who's in charge of these three buttons? You think I'm joking here, but who puts those three buttons there? Okay, whose job is that?
The window manager?
So, huh?
The window manager.
Okay, so this is a controversial debate. If the app does it, well, the app can have full control, because the app might want the app might want full control of how their window looks, right? But then it can be a little ugly if every app has something that looks a little bit different, or if an app doesn't want to write the code. So maybe you have the compositor do it, but then you have the opposite effect, where, hey, I'm an app, why can't I control this? Because so it's like there's no right answer here. So the big difference between Wayland and X11 is Wayland put the default as the opposite of this. They said the compositor could choose, and then X11, they flipped it and everybody got really pissed. So this pisses people off. So X11, that's the X11 is just an XML schema. You can like look it up. It's just literally an XML file. Like here's an example: set input focus. There's a little thing that tells you the parameters. You can use libxcb. Really quick, I found this out during his talk. Who knows what libxcb stands for? Anybody? It's libxc bindings. Fun fact for the day. Yeah, I didn't know. I was like, what? So you can use a function like libxcb that will just call the protocol for you. Cool. They call it X11. If you aren't aware, it's the 11th version of the X protocol, which they standardized 40 years ago, and it's still working today. Oh man. Yeah, so Wayland came in 2012. It's taken a long time to be a default, and there's still issues I find with it. But it's just built differently. You have this like zero trust model. Every frame's gonna be perfect, and obviously they built this in the 2000s, not in 1980s, so more focused on how people actually use computers in the current age. But these are just protocols. You can think like APIs. You still need someone to write code to consume it. So this is where compositors come in. The compositors consume these input from the protocols. I call these like the artists, because they're in charge of like the drop shadows and the transparency and the animations. That's the compositor's job. So next is the Windows manager. So the window manager, that's in charge of like, where is it on the screen? What's the size? Min max? Which one's on top of which? And if you're confused, it's because some people are both the window manager and the compositor, and sometimes they're separate things. It's very much a blurry line of who's responsible to do what. So, fun fact, go to your TTY terminal, run a command like this, dbus run session. I use, so really quick, dbus run session, that's like the, say, display to my monitor. Mutter is my compositor that I have installed on my laptop. And depending, you want to use X11 Wayland. If you do this, you get a blue screen. It's pretty useless. You can't do anything. They can't do anything. It's just a blue screen. But let's run a command after it. So kgx, that's the GNOME shell. That's like a just a bash shell. So if you do that, I get a blue screen, but at least I get a terminal. But let's do the Firefox. Same thing. I can run that. I get a Firefox. Well, these are different. So the one on the left, that's just running, which is with nothing, and the one on the right is different. There's, there's stuff at the top, there's this stuff on the bottom, there's this, the tab thing on the top looks different. Welcome to desktop environments. Okay, so desktop environments, this is what this is like the part that makes each distro look different. You put everything together, it's the thing that puts everything together. You put the little launcher over here, the blue border I had, that's a desktop environment's job. And that's where Linux has a ton of customization. Okay, so I know so we kind of lost ourselves from the GPU talk here. We've got really deep into the windowing system. So let's kind of like all put it together. So we have a GPU, it cranks out a nice frame of Doom. Okay, cool. I plop Doom onto my monitor. The next thing you're gonna need to do is you want to put up Firefox or something. So your window manager and all these all these things, you're gonna kind of get it all together, plop it over there. Maybe you want some fancy borders, your compositor puts a fancy border around it. Cool. This is like how you kind of put everything together. GPU renders just one of the many things that gets displayed on the screen. Who's ever used an FPS overlay to see how many FPS they have? Who's in charge of this? So this is what you have. You have a GPU rendering a frame, passing to my mutter, my compositor, which puts this to the screen. Where's the FPS overlay go? Anyone want to guess? Well, the answer is it could go anywhere. Like, you can literally bake it into the frame. You can have it as opposed to processing the frame. Mutter could just do it. You could have something that does it right before it gets pushed to the screen. Basically, this is why we can't have nice things when it comes to this stuff. Because there is no one's in charge of when things get put on top of each other. This is where a lot of issues come, is this everybody's trying to put pixels on the screen. They get put on other people's pixels, and they're like, hey, I had my pixels there first. What are you doing? This is where a lot of issues come in. Who knows the D word? Anybody know the D word? Driver. Yeah, you got it. You got a free mouse pad. Yes, drivers. Who's ever used Ubuntu with NVIDIA? and had bad problem with the drivers. Yeah. So what is this magical graphics driver that pisses every Ubuntu NVIDIA user off? So let's kind of give an example here. We have Blender, Vulkan, the driver, GPU. This is kind of the whole idea. So literally in Vulkan, there's a VK create buffer. That's a Vulkan API call. Blender, in the application, is calling VK create buffer. A graphics driver is just implementing that function. That's all a graphics driver is. It's just implement an API. Maybe you have multiple APIs, you have multiple drivers, one for each API. But that's all a graphics driver is. So imagine now, like you wrote your thing for DirectX instead of Vulkan. Well, what if we wrote a translation layer that would take DirectX calls and run it on Vulkan? And then maybe we take all like the audio calls and like the system file open stuff and do something like wine. We're 35 minutes in and we finally got to Linux gaming. Yeah! Woo! So Linux gaming. This is actually how Linux gaming like basically works. Okay. We were just talking about Proton earlier. Proton is like a collection of all these libraries. Depending if it's a Direct 9 game or Direct 12 game, there's different libraries to overlay it on Vulkan. It's going to pick certain commits of these repos, but it kind of just like seamlessly puts it together. And when you're on Steam, it like just just knows which one to pick for you. That's kind of the whole magic of Proton. It's just kind of the umbrella that put it all together. So yeah, this it works. And fun fact, if you watch this video, you find that it is faster to translate things on top of Vulkan than it is to just use the Windows operating system. Okay, so it is amazing how much faster it is to not use Windows. So yeah, going back to our apps, graphics driver, hardware diagram. Really, the graphics driver is built into two parts. There's a user mode driver and a kernel driver. Because like if you have Blender and Godot open, they're both trying to use the GPU. How does that work? Well, you have two apps. You have two instances of the user mode driver. You always have one kernel driver. The kernel driver has two jobs: allocate memory and synchronize work coming into the GPU. It's kind of your main two tasks. Okay, really quick, CPU world. A lot of people probably know about like LLVM and like you can take all your fun languages, get them to LLVM, and then you can output it to x86, ARM, RISC-V, all that. Well, GPUs have the same kind of idea. We have these shading languages like GLSL, HLSL, OpenCL. You get them to a thing called SPIR-V. SPIR-V is like essentially an LLVM port, but for GPUs. GPUs don't run x86 or ARM. GPUs all have their own proprietary ISAs, the instruction sets. So you give everybody when you use Vulkan, you hand over SPIR-V, and then all the graphics drivers on the fly compile it down to their ISA. Well, this means you need a compiler. So every graphics driver has a compiler stack that takes, so we have all that in there. So this right here, this is the graphics stack, the graphics driver. So when someone says graphics driver, they might be the compiler, they might be the kernel driver, they might be the user mode driver. Welcome to Mesa. Who's ever heard of Mesa? Yeah. What is Mesa? Mesa is a mega repo. Okay, that's how I best explain it. It started as a project to get like OpenGL drivers, and eventually they built like, you can get an OpenGL driver for like every GPU now in that repo. It's a kind of a build. You can build just the one that you want. Recently, then they added Vulkan, RADV. That's the name of the Vulkan driver that runs on AMD that the Steam Deck uses. That's a classic example. So the naming in this gets really confusing. So if someone just says the Mesa driver, it's like, oh, which Mesa driver? RADV. You're like, which GPU is that? And then the GL drivers have different names than the Vulkan drivers. The naming part's the one downfall. But yeah, no, this repo is amazing. It's been constantly improved. This is how we have graphics working on Linux. Oh, fun fact clock. Do you guys know what the fun fact is right now? Everybody wants to use GPUs. There aren't graphics. We have UI rendering, cameras, video encoders. They all want to use the GPU. So how do we share GPU memory? Okay, we have the camera. Let's take a classic example, which is you take the camera. I'm on my phone, and I have a picture of me, a video of me, and it's doing like some facial effect to make me look prettier, right? So it's got to do some GPU processing, and it's got to display to the screen. I don't know anything about cameras, but they probably have like a bunch of APIs out there for cameras. Has anybody worked on camera APIs? Is there a lot? Are they messy?
Yeah, I wouldn't work at that level, but yeah.
Yeah, okay.
Yeah, they're all different again.
Okay, cool. So, arbitrary camera API. You want to talk to Vulkan OpenGL to your GPU computation, and you want to use Wayland X11 to put it to the screen. what you don't want is you don't want to just be doing mem copies of all this memory every time. You would just want to be like, hey, everybody, it's on the GPU. Can we just all agree on where it is? Okay, that's like the ideal world. So with a buffer, that's easy. You pass in a pointer to the buffer and how big the buffer is. Yay. Images, oh my gosh, images. So everybody has to define a format. So in this one, PK format, this one's RGB, this is RGBA. So red, green, blue, alpha, each one's 8 bytes. It's unorms, it's a float value. It's an enum. So Vulkan, this enum is probably different than OpenGL's enum, right? And it's different than the camera API's enum. So they all have a different value, but they all kind of mean mostly the same thing. And there are so many formats. There are 8 bits, 16 bits. Who's ever seen like the gumbo thing from Forrest Gump? That's what it feels like. There's 8 bit, 16 bit, 32 bit, alpha, depth stencil, compressed for the GPU, ASCC, ETC, PC, YSVCR. Who's ever worked with YSVCR? That's your display displays RGB, but your cameras input YSVCR. And then you have to translate it over to RGB. So you have all these fancy formats. I worked at Samsung for a while. We have many of these. There are many of these YSVCR formats. The camera app is the most, of all the apps on your phone, the camera app has to be the most like money spent on any app. You'd be amazed how much money they spend on the camera app. So yeah, getting everybody to agree is incredibly hard. It's a lot of we call it interoperability. Make sure everybody agrees that this format is this format. Okay, I have this RGB format. What do you call it? You call it that. Cool. It's a lot of plumbing. It's a lot of plumbing. I wish it was less, but this is where a lot of things get annoying. Yeah, this is where sometimes I feel like I tell people I love 3D graphics, and I start explaining all of this, and they're like, "Are you sure you like it?" So, yeah, that's all I got for you guys. Oh, did you guys hear that? It's the bonus round. Yeah. This is the part of the talk where I try to answer your questions before you ask them, okay? First one, the GameCube. I found about this yesterday. I don't know anything about it. Sorry. I know the headset is running. Is going to be running a Qualcomm Mesa driver, the turnip driver. So yeah, Valve's doing well. I hope GameCube sticks. Sometimes you can ask, which GPU is faster? This is a terrible question, okay? Like, we had this joke, like, we could build the Fortnite accelerator if we wanted. It'd be so fast at Fortnite, it'd be so bad at everything else. So, like, if you're benchmarking your GPU, just know benchmarks, I call it necessary evils. Like, we need them because we don't have a benchmark of nothing to, like, compare against, but they're just one data point. Like, you just have to, like, get a workload you care about and try 2 different GPUs to really know if it's faster. Because again, it's trying to be good at everything. So and they have a weird like chicken egg battle where apps try to make it faster than GPU, but then if you're a GPU company, you make sure the best apps work well for you. So you kind of have this weird chicken egg effect. Another one I get a lot of times, someone talking about their teraflops, whatever. Teraflops don't mean anything anymore. If you're unaware, flops stand for floating point operations per second. I said before, things are memory bound. Like almost all the tricks that they use now for GPUs, almost all the issues is because they can't get memory in and out fast enough. So like people are most likely not constrained by how many flops they can crunch on their GPUs these days. Another one I get a lot is, well, Vulkan, is it faster than it's okay. Vulkan is not about being faster or not, it's about giving you control. You can like write slow code with Vulkan because it's just giving you control of the GPU. You can write bad GPU code. People write bugs all the time. But when you hit the bottleneck, you can fix it. This is kind of like the whole like why Valve likes to make their own drivers is they want to be in control. Like some people want to have control. Well, we're not a Linux user group. What am I talking about? Like, who am I trying to explain control to? So next one I get is why Vulkan is complex. If you ever hear like things online, it takes like 1,000 lines to write a triangle. I'll tell you right now, Vulkan could be so much more complex. You could add as someone who works on the Vulkan working group, we could add so much more. When I was at, the AMD open source compiler, if you do -- help, it literally gives you like 100 options, and at the end it goes -- more help. I'm like, what? There's like 300 options, and we expose like a generic, just one. We have like a default that we expose, but there's like 300 options in here we're not even exposing. So yeah, it's not complex enough. as it could be. And we've only made it more complex in the last 10 years. CUDA's the favorite one. If anybody, CUDA, it's a thing that's brought up all the time. If you're unaware, CUDA is a compute only, it's not graphics, only compute, and it's a vendor lock-in. So the big advantage is you get a lot of really good tools and years of ecosystem support. The downside is you're stuck you're in vendor lock mode, and trying to translate on top of CUDA is not really a successful thing. So it's like pick your poison. What do you want? Yeah, cool. That's all. Okay, that's actually the talk. Before I go, I want to say really quick. I brought this from our office last time I was there. After the talk, I have some stickers and one mouse pad. Whoever gets here first. But yeah, this is where. Fair. Cameraman, he's working today. All right, so we're open for questions. Anybody got questions? Go.
Where can I get that t-shirt?
This t-shirt?
Yeah.
They actually stopped making the t-shirts because the person in charge didn't like spending money on it, so they're kind of a rare commodity now.
That's all right.
You didn't talk about security at all.
Because game development.
Does Vulkan deal with security, or is that done somewhere else in the stack?
So, I don't have it. It's the big one who cares. Okay, security. Okay, a classic thing we done in security is robustness. So, you have a GPUs. If you try to if you have a buffer that's 256 bytes, and you try to, read memory out of it, the GPU can detect that and zero it out. They call that robustness because it will make sure if you're out of bounds, it will prevent that value from being noticed. There's a 3% performance hit on it. So it's a lot of people don't, if you're a game developer who's I don't want this 3% performance hit, they turn it off. Who loves this is WebGPU, WebGL. That's a huge attack vector. So Chrome has this whole thing about how they control every part of the Chromium stack except when it gets to graphics drivers. It's kind of oh nope, not our world. So there's a lot of stuff that the WebGPU, WebGL does as an API to really lock down the GPU. I always joke that graphics programmers aren't smart enough to get a GPU to work. I don't know how security researchers to get a GPU to work. But no, at an API level, I mean, we have we add things like zero initialization. We have stuff like that. But at some level, there's an app responsibility too. So.
This might be sort of a loaded question, but why are NVIDIA drivers so more complex than any other driver basically?
So I think as someone who worked on drivers, I think what happens a lot is you have this hard issue where you make a new generation of GPUs, and I don't know what NVIDIA does, but when you make a new generation of GPUs, do you just say we're gonna start over, and maintain two code bases, one for each driver, or do you try to make a commonality thing? I know AMD, one of their issues they have is that they make a driver for the PS5, the PS4, the Xbox. That's not code that goes into the desktop AMD card, right? So and sometimes you make these deals with people that you're gonna give them the source. So when Meta made their headset with a Qualcomm chip, I guarantee you they got sourced to Qualcomm's drivers so they could debug it, right? So now Qualcomm has to make sure there's no reference to Meta anywhere in their code if they do it with another customer, right? So I think what happens sometimes is over the years of having multiple GPUs and all this stuff, people's drivers get more and more complex, and then you just start duct taping it, and it's hard to ask your manager to rewrite your code. No one wants to rewrite everything. So I'm assuming that's where a lot of complexity comes from, just years of new hardware coming out and having to keep it all together. So.
When vendors decide to get a little special with their hardware, do they usually come in and do the adaptation to make it work with Vulkan, or do they just?
So let's take ray tracing. Ray tracing, if you aren't aware, was a thing. Ray tracing as an algorithm has been used forever. Ray tracing as a GPU accelerated feature was relatively new. NVIDIA came out with it. What they did is a generation before they released it, they actually used the extra die space on their GPU to put it in so they could test it. And then, so they're testing it, and they'll come and they'll to the working group and they say, hey, we're having a new GPU coming out that's going to be using this. So they create like an extension for the API. So it's kind of like, I mean, eventually, everybody inside the Kronos group, we're all under an NDA, so we can't like, I don't think how many people really care anyway. So I always joke that I spill it. I can tell so many people what we do at Kronos, but I don't think anybody really cares. It's the average person. But so kind of going back to your question, when people have special sauce or whatever, they just, it takes so long that even when they say, hey, we have ray tracing, if someone's not started, it's going to take years to get that in. Because if they just release a card, if you release a card every year, they're starting to work on the 2028 card now. So it's like, it's such a long cycle that even you say, oh my gosh, we gotta start right now, it's still gonna take 2 years to get it into a proper GPU.
Thoughts on unified memory, like in laptops especially?
So, okay, desktop, as I talked about, so desktop, you have a separate graphics card. And so when you wanna put memory from the CPU, to like your normal RAM, to your GPU, you have to go through the PCI Express bus. If you're on a phone, there's a single chip. So the one advantage of mobile, they call it unified memory architecture. It's where it's the same memory. So the difference is the kernel will put like a special tag on it saying there's a GPU memory and there's a CPU memory. But it's just, and then there's nothing to say other than it's faster because you don't have to spend time waiting for the PCI Express. The problem is usually when you're on a single chip, you're power constrained. So really quick, the reason it's not like NVIDIA is way smarter than the Qualcomm engineers making the mobile devices that they can make their device faster. It's that Qualcomm, the mobile vendors, and Samsung, and ARM, they have like 2 watts of power to deal with. Like wattage is a big thing, where NVIDIA cards take like 200 watts. So it's like, you pick your poison. If you're on a unified memory architecture, most likely you're not in a high wattage thing. So even though you have a faster memory bandwidth, you're gonna be just lacking power to like utilize a faster GPU. So, but no, as a developer, it's nice you don't have to like do this copying. You can just know it's right there. So you just send a pointer somewhere. It's, oh, cool. Any other questions?
Sometimes, I think you mentioned it too,
Oh.
that sometimes you hear that with a particular application, Vulkan is actually just faster than running the native drivers. And I always thought that was kind of fascinating to other people because it's just shim in the middle of things, but it turns out people are doing little tests and they go, oh yeah, my favorite app runs faster if I run it in Vulkan instead of Windows or these drivers.
I mean, the shims are, depending. Like, there are definitely, I know that they do some crazy workarounds to get things just to work, but like a lot of the difference between these APIs is not that much. I mean, they all do the same thing. They allocate memory, they push this, they push stuff to memory. It's not like that drastically different. Like, you just have a little bit of extra, 2%, 3% hit compared to like your OS constantly deciding to run stuff in the background. Like, yeah. Any other, sorry, you got it?
Just a comment more than anything else, but you triggered something in my mind when you started talking about X11 and being able to do remote. So it reminded me back in the late 80s, there were a whole bunch of companies building devices to be able to do just what you were talking about, being able to render X11 apps and things on a smaller, much less expensive device.
A terminal.
Yeah, the X-terminal world, that's what they call. And I actually got to test a few of those when I was working at Lockheed back in the late 80s and play with them. And I still find myself occasionally doing a remote display of something to another system.
There's a whole debate about, especially, Qualcomm. You're aware Qualcomm's a semiconductor, some fabless semiconductor in San Diego. They make the chips for a mobile device. They invented like 5G. So they're really a 5G company who has a GPU. So there's a bunch of debates inside. Should we make our GPU faster, or should we make 5G, 6G so fast that we can just send the frame, like we just render it on this laptop, and then when I'm like a headset, it can just send it super fast because we'll have such fast 6G. So there are still people who believe, wireless people who still believe, we don't need a powerful GPU on the mobile end. We'll just stream it.
Since there's a bunch of Linux folks in here, I would challenge you to go try it. Just go through the process of actually displaying a terminal on another device from, say, your
Sounds
laptop. And it still works. It's still kind of cool that you can do that. The protocols are still there, and you have to set a display variable, and then you typically have to run Xhost Plus over on the other thing, so it will actually accept your window coming from another device. But it's kind of cool. I mean, I still mess with it from time to time. I find I haven't had to do it for a while, but there's been a few cases where I've needed to do that. Especially like using an old browser from a server back to my laptop, so I don't have to get up and walk across the room for whatever I was doing. It's kind of neat.
I have a quick question.
Oh, yeah.
You were explaining that on the CPU you have memory laid out one way, and then the GPU might be in a completely different way.
Yeah.
Is it Vulkan that's responsible for, like,
So
some layer of Vulkan?
Vulkan has a concept of linear and optimal memory.
Okay.
So you create an image. So what you do, if you're an app developer, you load a JPEG up from memory, you put it into a buffer, right? You malloc some memory, you put your JPEG memory in there, and then you're going to copy it to a linear image.
Right.
So that's the one that you understand.
Right.
And then you just do a VK command copy image. So you just copy the image. You allocate so you query. What you do is you're going to query the driver. Say, here's my height, width, format.
Right.
How much memory do I need? I need that much memory? Cool. You allocate that GPU memory, you copy it over, and now it's in optimal GPU tiling. If it's not,
And Vulkan is what does the
Vulkan gives the app the ability to do that.
Okay.
So in OpenGL, you didn't have this ability. It just kind of magically happened for you. In OpenGL,
Right.
this kind of just happened. So like, there's like GL read pixel, where you want to like, what's the color of this pixel? And underneath the hood, the GL driver is like doing this for you. It's, oh gosh, we gotta bring it back to linear and then give you the color. It's really slow. It's a bottleneck for a lot of people. So in Vulkan, they were like, you just do it. Like, you do it. We're not doing it anymore. You do it. That's kind of like, that's a classic like trade-off between like OpenGL and Vulkan. It's like something like that.
Do you think running video games in the web browser will ever be like a thing that's a common platform? Because I remember when web GPU was first like finalized and started becoming a standard in browsers, this promise of like, oh, all your games will be cross-platform, they'll run all in Chromium or in Firefox, and that's not the case.
I don't know. I think part of it is that game development is like one of those. Okay, you know how we're still on X11, it's been 40 years. Game developers aren't too far away from like not wanting to adjust their workflow. I think the problem, a big issue with game development is if you're a big game studio, there's what they call the graphics, the artist pipeline. So someone's making the art, someone's making the models, you have this whole system, and even if you're using like Unity and Unreal that can technically output it to WebGL, WebGPU, I don't know, I guess there's just no appetite for it.
Well, also, you have to code the rest of the application too.
Yeah, you still gotta build the rest of the application and
if
JavaScript.
you're gonna do that in JavaScript, that would make suck.
Yeah.
Maybe.
It'd be slow. Yeah.
They've got a solution for that.
Yeah,
JavaScript
sure.
just run binary.
So.
Yeah, I don't know. I'm curious too. I guess it just hasn't panned out. I also don't know where you sell it. And then another thing, where do you sell your web GPU game? Like, it's not like a Steam store for it. Like, how do you sell it?
I could make that happen. That's not sure.
But yeah.
The binary would have to live on your computer, obviously, because things would be like loaded in with everything.
Yeah, it'd be like you have to load every time. Yeah. Can't play it
Ship people
offline.
Chromium.
I actually don't know why the industry has. I know I'm always waiting for this like explosion of like web-based games. I just haven't seen it. Like, I feel like we have more Flash games available than like web GPU games.
I tried like FFmpeg once in a web browser. It was like 10% as fast. It was like ridiculously slow. It's not good.
Do it.
Yeah, I have a serious question this time.
Oh.
Oh no, like no, like.
Yeah, what is it?
Yeah, so like you said, each vendor implements their own like quote unquote instruction set for GPUs,
Yeah.
right? I assume like this is true for like all of them, right? Like for NVIDIA, for
Oh, yeah.
AMD, of course, but also for Qualcomm and Samsung and stuff. Like, is there any possibility to like define a standard architecture?
Zero. Maybe zero chance.
I'm not asking like practically. I'm not asking politically. I'm asking like, does it make sense physically or like architecture-wise?
No, it's gonna take. We're at the stage where we still wish they could all open. And actually, I'll give AMD credit. AMD is actually the best at opening their ISA, so you can actually go and find all their instruction sets, like all their instructions. A lot of it is just like things like, let me find a random one. Like a scale. Okay, it's like scalar, ALU. ALU's adding, subtracting. So, we're not getting into scalar vectors, but yeah, they have this. I think so. What we do in the working group, we have SpearV. SpearV is like LLVM. That's pretty good actually. It's pretty good. Like it gives you enough of a like high level, low level like compromise, because at some point there's just when it comes to ISAs, people make some crazy random ISAs. Like you make such like what was I looking at the other day? It was like this. It's like wave multiplier 16 by 16 by 6. I might have it here. It's crazy what people add in these ISAs. I just can't imagine they'll ever have a way to standardize it. They just need it. So
I mean, it's kind of the case for the CPU side, right? Like people, like I mean, AMD needs to follow x86, 64, like you can follow AMD or RISC-V.
yeah, like, wave multiplier, math multiplier addition, 30-bit, 6 by 16 by 16, float 16 or B float 16. Like, yeah, it's just no. I think the industry first thing we need to do is get people like open source their ISA before we even like attempt to standardize it. I think it's going to take a while. So that's the GPU industry has went from everything being closed guarded. Basically what happened is over the years everybody thought they had like secret sauce and they were hiding it, and slowly people were like, oh, you do the same thing? Okay, oh, we do the same thing? And slowly we're kind of like all agreeing that, oh, we all just have the same thing and just, it's not that special. And everybody's kind of been slowly opening up more and more. So we'll get there. Maybe one day we'll get there.
Hopefully.
So you mentioned that your major sponsor is Volvo?
Valve?
Valve?
Yeah.
Okay. I'm sorry. I thought it was Volvo, and so I was
That's just
like.
my speed talking, sorry.
So I was like, are you? I mean, in my head,
I don't even know
like,
what
are
company
you,
it-
are
what-
you like training one of those robocars? It's
Oh,
not-
no.
I was thinking Volvo. I was like.
No, our main sponsors are the software people are like Google and Valve, who just want an ecosystem to work, and then all the hardware vendors. It's again classic. Again, it just goes to there's these tools that everybody uses that in between the hardware and software, but no one wants to like pay to like just keep it, and so but they'll. It's really easy for a company to like give a check versus like hire someone. It's much easier for a corporate company to be like, yeah, here's a check. Want to hire someone? No. Listen, we're laying off. Well, here's a check. Like, it's crazy.
So are there a lot of other companies like yours
Yeah,
that do what
like
you do?
so there's like one like Angelius. They focus more on like Mesa drivers.
Mhm.
So they do like kind of like different areas. There's like yeah, they're kind of like.
And are they also kind of small, like they're?
Oh yeah, like, there's like
they're
20,
specialized, yeah.
20-ish people. They're not like it's not a growth, not a
Right,
it's
right.
not a blue chip growth company
Yeah.
by any means. Oh, here you.
No, you go first.
Oh, you're
So I was looking at the Vulkan tutorial today to prepare for this.
Mistakes.
I noticed it was talking about Liturgy.
So we make the SDK. So the
Okay.
big thing we make is
So it's
Liturgy.
like
We make,
entire SDK.
so you can go build. There's so many things. You gotta get the headers. You gotta get the validation layers. You gotta get your tool to compile your shaders. You can kind of like we build every 2 months. We put together all the tools, tested it, and put it together. So that's kind of that's the main like thing we're branded for, is that we build all the components.
Yeah, all the
and like
tested, cubes. With
that's a classic one, like the VK cube. Like that's our is everything working? Like that's our quick like smoke test if things are working or not. It's like we get the cube to display.
So what else does Liturgy do with Vulkan Uploads?
There's a big half our team, not half, a third of our team works on a tool called GFX Reconstruct, which is there's this whole issue that vendors really want, which is you want to okay, you had the app graphics driver hardware. You want to eliminate the app. Like you don't want this. Let's say you want to like debug Doom. You don't want to be like starting Doom every time and have to like get to this level. What you do is you trace it. So we literally just capture a tool that captures all the API calls, all the memory, and save this in a file. And then you can like delete Doom, and then you can just replay this. It looks like a video. It looks like a video. Okay, you know what? We'll do it live. See what happens. I was trying to debug something. No. Oh yeah, here we go. Let's see. Let's see if this works. Oh, I gotta do it. I'm not. So what it does is we've traced it. We've like captured all the content in a file, and then we're just gonna like. It looks like a video file. So this is like it looks like a video, but really just replaying. It's just replaying the same command.
It's just playing the
just the API?
Yeah, it's just literally redoing the API. So we don't need the app anymore. We can just take a single frame and like. Yeah, and so like people love this, like vendors love this because when they're building hardware, they have hardware simulators and they want like one frame. They don't want a whole game. They want one frame to test because it takes an hour to run on a hardware simulator. So they want like we have a lot of hardware people who pay us just so we can like keep this tool working. So they can like take one frame and like just replay it over and over again. It's deterministic. That's a big advantage. It's a deterministic replay. There's also things to kind of make it work between like, so you can capture in one device and play on another device. That's like a big common thing. That's like one thing Liturgy does. A lot of the rest of it is just ecosystem tools, all the tools. Like someone's got to maintain them.
Now I gotta ask, how efficient is that format? How much disk space is it taking?
Let's
right
find
now?
out. That was 3 gigs.
You know it's cheap, you know?
I mean, it takes. Okay, so yeah. Oh my God.
Well, you're storing all of the.
Well, the problem is, we only capture the GPU API calls. What if they call memcopy, and like onto memory that's being like mapped? So we have like things that we like track virtual pages and like store that. We don't know if they touched it or not, so we're like, cool, like save it.
Grab it all.
Grab it all.
So the purpose of having that thing is that they can like recompile the shaders and then run the same.
Well, the idea is that we can play an app deterministically. We don't need the app anymore. We can just rerun the app every time, and you've eliminated kind of like you're debugging. You're debugging. You're eliminating a variable. Like, hey, I can replay this every time. So I want to do performance now, right? How fast? Like I work on a tool, a debugging tool. I'll take a trace, run it, 20 FPS. My debugging tool, oh, it's 2 FPS. Ooh, it's really slow. Like that's the use case right there. So it's
unit testing.
Yeah. Oh yeah, people put in their like test farms to make sure like, you can render it and then take a picture, maybe make sure like your driver didn't regress. Like another one you can do is, I do this all the time with the Mesa people. I'll be like, hey, your driver's broken. Here's a trace, and they go, oh yeah, I can reproduce it. And so that's a use case. Yeah.
Okay. I've had to deal with virtual or GPU virtualization and VDI stuff at work, and does Vulkan play a role in that at all, or opening that very proprietary? It seemed like it was all very proprietary.
I think so. Chromium has a Mesa driver for this. I don't know how it's for their Chromebooks. They had like some. I don't know.
Chromebook, you're on a like game in the cloud. Use a
They made
GPU in the cloud.
They wanted to be Chromebooks. They had a whole effort to make gaming on Chromebooks a thing.
Yeah.
So they built like this. It's like called virtual. I forget what it's called. It's starts with a V. It's a Mesa driver that's designed to do virtualization. Virtualization is out of my league, but I don't know. I actually don't know how. I imagine it's just calling Vulkan. I really don't know. I couldn't tell you. I'm sorry.
Sorry. Curious. I'm like,
Thoughts on WGPU?
So WGPU is web GPU, right? WGPU?
Yeah, just WGPU. The Rust.
Oh, no, okay. Web GPU. So I talked about WebGL and WebGPU. WebGL, there's WebGL, WebGL2, and instead of WebGL3, for reasons they made WebGPU. Okay? WebGPU has implementations. So Chrome has implementation, Firefox has implementation, Safari has implementation. Chrome's implementation is called Dawn. Firefox implementation is called WebGPU. WGPU. The idea of it is that you're kind of talking about like the game developer thing. So the idea of WebGPU, and I've not played around with this, is that you can do it both you can write it both. They made like this API so it could be a JavaScript API and like a C++ or Rust API. So the idea is that same level of abstraction, but it will have a JavaScript input and then like a native language input. So that's what WebGPU is. WGPU is. It's Mozilla's Rust implementation of the WebGPU.
But I think it sits on the actual native graphics API.
So it's calling Vulkan.
Yeah.
They come into report issues all the time. They find issues all the time. The WGPU people are very active. Like Linux users naturally are just very like, I don't know, Rust Linux people are very, very active to create issues. So yeah.
Okay, sorry.
Go ahead.
This is,
Fine.
kind of new to me, so maybe this is a dumb question, but I assume that there's some algorithm that's trying to optimize like between software and hardware, and like basically, I mean, one, reduce memory, or like speed of inference, etc. Right? So I'm just wondering if you have all of these different naming variables, how do the algorithms work with that?
What do you mean by naming variables?
So you showed earlier that spreadsheet of like all the different ways that the APIs are connected and all the other hardware stuff. Like, again, this is new.
No, it's fine.
There's a slide that had a ton of different names, and then you showed the AMD website and had all these specifications.
Oh.
So I'm just wondering, well, if you're trying to run an algorithm to
Okay, the people,
speed up
the
inference or save memory, how do you do that if you have
so
all these?
people are not using this. This is what the driver people are using.
Okay.
So this is like what driver people are using.
Okay.
Okay, this is like, you got, like, there's a layers, right? So you have the hardware, you have, to program it, you need an ISA, but you're not gonna use an ISA, you're gonna use what I talked about here, this.
So I guess my simple question is, if you're trying to speed up inference, then do you, like, what I've heard a lot is there's a ton of different names and it's hard to sync up between software and hardware. So if you're trying to speed up inference, does any of that matter? I guess is really my question.
I think, when you say speed up inferencing, you mean like you have some algorithm that runs on a CPU?
So like for gaming, because I'm
Yeah.
actually, funny enough.
When you say inferencing, you mean like AI inferencing, right? That's what you mean by inferencing?
So I actually do talk to gaming people. I actually don't game. I don't know anything about gaming, but
That's fine.
I do talk to gaming people. And like one of the problems that they say is that they're trying to solve actually is the frames.
Yeah.
Like they want the frames to like speed up. So you need an algorithm to do that. I mean, there's several algorithms to do that. So my question is, if you're running all these different algorithms, does that have anything to do with
So
this?
you're talking about super scaling, I think. So super scaling is, who's ever heard of like DLSS? Yeah, so there's this whole idea that instead of rendering at 4K, you render your image at a really small, like 720, and then you upscale it. So you use an AI inferencing to like, if I take an
does
image.
that have anything to do with this?
Yeah, no, this is a big thing actually. So like, if I take this image, if I just expand it really big, I just stretch it really big, it's gonna get pixelated, right? Because the image itself is a small image. I'm trying to it's gonna pixelate.
Right.
So what you do is you use an AI algorithm to inference like how it should look. You want to scale it up from like 1K from 1080p to 4K, but it's gonna look pixelated. So you run the AI algorithm on it, and it looks not pixelated.
There's some cool YouTubes where they show somebody doing a video at like, I don't know, 800 by 600, and then they said, run our stuff, and look, it's 4K now.
Yeah, so like.
So is that running on, is that the super scaling running on the GPU then?
So super scale is a whole issue right now because everybody has their own. Like Nintendo Switch has their own, AMD has like 3, NVIDIA has like 3, Samsung has their own. Like everybody has their own like AI that they've trained to do it. What you do, how this works is it's like a 2-step process. The first step is that and so trying to go back to your question, like the whole idea is you can get things faster by just you're rendering it to a small, less pixels, or you can render less pixels faster, right? Like you can render a 2x2 image way faster than a 4K image. So it's like finding the balance of how small can I render it that when I use the AI to blow it up to the full resolution, it still looks good. That's like the whole like new evolution of like graphics techniques.
And it runs fast enough too.
Yeah, and so what you do is you usually train it on your game. Usually what you do is the thing has to like play your content, and then it's gonna like train on that, and then you can run it. Then you have the inference library, and it can run it. It's a whole issue right now, like because everybody has their idea, and there's no like common way of doing it.
And that runs on the GPU though, the inference?
Yes,
Okay,
the inferencing.
yeah.
Yeah, sorry, the inferencing will run on the GPU. Like they'll run. I mean, that's its own library though. Like they might like AMD has a Vulkan compute version. NVIDIA probably does it in CUDA. Like they might just do it in their driver. Like I don't know how everybody does it different.
So is there any appetite or intention of Vulkan incorporating part of that into its specification, or is it all
The super scaling?
Yeah.
We tried at our last working group, twice a year, we all meet, all the companies meet in person, call it face-to-face. Someone brought it up, and we all agreed to disagree, like, we all agreed that we don't want to standardize it, 'cause we don't have, it's not ready. When things are constantly being changed, it's not a good time to try to standardize it, because you're just gonna be stuck supporting old things that no one wants. So it's such a rapidly changing thing that no one knows the answer to yet.
So that's why every game kind of has to have a specific option to call this particular function, this particular driver, or this particular function, this particular driver. That's why the options are all spread out.
Yeah, and I know like companies like NVIDIA will work with these companies. Like that's like a thing too. Is like how do you make DLSS good? You pay a game studio, use this. Like, okay, cool. So game studios do fund themselves sometimes by having they're a big studio. You know, it's a chicken egg problem. Like obviously games want to work well on hardware, but hardware people want to make sure games work well on them. So it's like, hey, use this, we'll make it faster. We don't have time for that. Here's money. We have time for that. Cool.
Just found the time.
Oh.
Oh, it's a very open-ended question, but could you just talk to, especially because it's the time of year to do it, is there's this explosion of new graphics cards, capabilities. You know, somebody who's an outsider, it's hard to follow that. Like, oh, AMD's doing this, now Intel's doing that, now NVIDIA's doing the other thing.
There is like so much stuff that people try to there are so many things. It's like sometimes the hardware people have this, if we build it, they'll come attitude. It doesn't work. People add things all the time. Like when ray tracing came out, there was a big thing like, will people actually go to ray tracing, or is this just kind of like cool? But like, it's just like the transition to use it.
Yeah.
And there's a lot of energy to like, you know, rip off, redo all your code on this new thing, and it'd be like, oh, it's actually slower. Like, so I think when they add these new features now, they're all trying to find like a cutting edge, I guess, and they all try to find it in different ways, and they always put demos out that look great because they're little demos, but no one, you still gotta get a bunch of apps to use it. What?
Since NVIDIA's like all in on the AI, do you actually see less participation with them with the gaming companies now, or
No,
is that pretty good?
they just have, I think how I understand from talking to people in NVIDIA is, as the company as the AI bubble has blown up, the graphics team has just like stayed as normal, and there's just like whole new divisions that have like kind of grown. But like the graphics, there's still the same people there. Like they haven't like, they didn't like take the graphics people and say, hey, go do the AI now. I think they just hired on new stuff, and they kind of kept the graphics stuff going as it is. But there's like a lot of AI stuff coming through Vulkan now. It comes in forms of like that weird, I was just showing here that like stupid instruction. Like we have a thing in Vulkan now to do fast matrix, what do you call it? Math, matrix, apply, divide, or like they have like FMA, floating multiply addition. Like we have all these things like that. They have a term called tensors, like for tensor boards. All a tensor is, okay, ready? 2D image, 3D image, XD image, that's a tensor. A tensor is just an XD image because algorithms don't want to use multi-dimensional stuff. So they had to create like a tensor, which is, I remember the first time someone saw it, they were like, isn't this just a 4D image? No, it's different. I'm like, oh, okay. I'm not the AI engineer.
I'm gonna ask you a real practical question.
Oh, man.
If I had $500 I was gonna budget to go buy a GPU, what would you buy?
What do you want to use it for?
Gaming.
Okay. Everyone just mind this. Are you on Linux or Windows?
Oh, it'd probably use both.
If you're on Windows, NVIDIA. If you're on Linux, AMD.
Yeah.
That's my suggestion. If you're on Windows, go NVIDIA. The AMD Windows driver I hate. It causes us a lot of pain. But on Linux, man, the AMD, like Steam has put, the Valve people have put a lot of energy into the AMD. Like this is AMD. So this laptop right here, this is an AMD. This is essentially the Steam Deck, but as a laptop. Man, games run really well on here. Okay, I can tell you right now. Like this is even just with the integrated graphics. Like AMD Linux is doing a great job, in my opinion.
That's great. Thank you.
I'm going to ask an impractical question. I know we got a graphics platform here, but if I wanted to write my compute algorithm to like detect red boxes or whatever on it, how much would I need to be abusing the shader system to make that work?
Well, if you're running, okay. So I talked about like the depth buffer and the vertex buffer. If you're just doing compute, it's two things. It's like if you use CUDA or OpenCL, it's literally just allocate memory, run my shader.
Right, yeah.
That's all it is. Like, there's no graphics pipeline. There's none of that. So it's just shaders at that point.
Mhm.
It's just all it is. It's just compute shaders. So.
So the answer is just skip the Vulkan, go straight to the shaders.
Well, you can do Vulkan compute. So in Vulkan you can do compute or graphics.
Oh, okay.
Like Vulkan, when you create a compute pipeline or a graphics pipeline. So you can just do pure compute. Like they call it headless Vulkan. So you don't even need you can like have no monitor. So the Vulkan specification does not require you to support a window, because they wanted people to have compute only usage of it. So actually the big one is, okay, here's one for you. CL Spear V. So this project, Adobe has apparently 5 million lines of OpenCL compute kernel code. Okay? Yeah. And they were gonna ship this new, I think it was called Adobe Rush. This is like 6 years ago. It was gonna be this cross-platform video editing, okay? Really here, you notice this? Cross-platform? So Pixel 2 or 3 came out. The Pixel 2 or 3 came out. And the Pixel people got rid of OpenCL. They didn't want to support it anymore. So it was, when I say we got rid of it, you could take the driver from another phone, put it on the spot, and it would suddenly work. Like they literally just were like, we're not supporting this, RM. Like that's all they did. So then Adobe was like, WTF, we need OpenCL to work on Android. We're about to ship this 5 million lines of kernel code. Because it's just compute. It's just compute, a bunch of compute algorithms. That's all it was. And so they built a thing called, Google made this project called CL Spear V, which takes CL, OpenCL, and just translates it to Vulkan Spear V.
Mm-hmm.
So they use Vulkan as just like the cross-platform API. They write their shaders in OpenCL, use this tool to get to Spear V, and then so it just looks like a Vulkan app. So you can just do compute and like Vulkan. Like, yeah, it's just, at that point, you just depends what shading language you want to use. And we've made it, like, if you have a diagram, we've made every possibility work. Like, if someone wants this path, oh my gosh. People do some crazy stuff with their shader compiler pipelines. But,
Do you happen to know, are there some wrappers too around Python or Rust or something to do that compute without?
so the big one I know is, so Slang is the new player on the block. So Slang is a terrible Google search term, so you gotta like do Slang GPU. It's this new shading language, kind of like GLSL, like the shading these, and so it's designed itself to be a shading language. And they built this with AI researchers in mind, and AI researchers like Python.
Yes.
So they built this. Another one that's been really big is Mojo. Mojo's the guy who invented LLVM. He got a bunch of venture capitalist money to like Chris Latner. He invented LLVM. He got a bunch of capital investment funding to work on this project, which is they made a superset of Python that goes straight to the GPU. There's all these ideas of like, do I write Python and it magically runs on the GPU, or do you make the person have to learn a little? They went the approach of, you're going to use Python, you're going to understand a little bit about GPUs, and by doing a little bit more.
They know you up there. Yeah.
Yes, and so they've done that.
I haven't done much of that, but if you know a little bit how the GPU is, set up your matrices just right, then it goes in better and runs faster.
Yeah, the thing with compute though is like, sometimes it's like, what's my goal to make this faster, right? So you need a large amount of work, and then you need a way to like benchmark it essentially. So if you don't have a large amount of work, then it's not as useful. Any other? Yeah.
So I watched like a lot of graphics content. They talk about like running code on the GPU. Is that?
That's a shader. That's a
that
kernel.
only through
That's
the shader. Really?
when they say running it on the GPU, the shader, the kernel, those are that's again, think of it like a C program. You compile it to LVM, it's Clang, whatever, and it gets into a binary with x86 or ARM. The GPU, you write it in a shading language, you run it on an NVIDIA machine, so it gets down to NVIDIA's ISA, and it executes on the GPU. Like, it just looks like instructions, like it looks like assembly too, like it's just, yeah.
And that's where you ran into what you showed earlier, you've got to move data back and forth, and it takes too long just to run your CPU.
Yeah, that's the thing, if you have such a small task, it just won't matter, you don't waste time, it'll be slower. You have such a small task, you gotta have like, something that takes like minutes or something, then you'll find it goes from like 5 minutes, if it goes from 10 minutes to like 30 seconds, that's like more of a good thing. The question in the back?
This is a even less practical
That's
question.
fine.
But so I've noticed in a lot of benchmarks lately over the past few years. I've been seeing changes in them using FP16 to like FP8s. How long do we see FP4? It's already here.
It's already here.
FP4 in like actual benchmarks.
So really quick, so floating point traditionally is, so GPUs started out as not just floating point machines, but 32-bit floating point machines. That's what they specialized in. Researchers wanted like 64-bit floating points. So there are 64-bit floating points. That's a lot of researchers who, you know, if you're calculating the distance from me to Mars, like a small difference is you know, it's like a few hundred miles. But with like inferencing, like AI algorithm, they've been slowly learning, hey, we don't actually need 32 bits, we only need 16, and now we only need 8, and we only need 4. And so we've developed 8-bit, 4-bit, so yeah, we have those out there. I don't know, there's not like a big use case. The biggest problem is for like a lot of games, that's not like the problem, I guess, and they need that floating point precision. Like it's too little, so like games don't want to use it. They had a thing. Here's a fun one. They tried to add a thing for 4-bit ints. Okay,
Yeah.
what's the size of an 8-bit int? 1 byte. What's the size of a 4-bit int? Like it's like, oh, it's a half a byte, and so yeah, that didn't work out well. That broke everything. And it's like, so. No, we've been slowly lowering. We have support for it. I mean, it's also like a benchmark thing. Like some people have found that, you know, these GPUs are still designed to crank 32-bit floats really fast. So if you're a GPU vendor, do you just give that up to make sure you can run 4-bit floats really fast? It's like it's again trade-off. Like you gotta make sure everything works well.
So question, so NVIDIA, for example, is always pushing out new drivers whenever there's like new games that come out.
Yes.
And they're like optimized for all the different kind of games.
Yes.
When new software comes out that people shouldn't typically run, like emulators,
Yeah.
morally speaking, these companies, like, you know, Nintendo doesn't like when somebody pushes an emulator out. So when the Switch 2 emulator comes out and there's inevitably like issues and stuff, are companies like yours and NVIDIA gonna run this software, which Nintendo hopes is illegal?
Okay, really quick, I'll tell you right now, the emulator people are the most passionate, strong-hearted people I've ever met online. They will go great length to get things to work, great length. The Yuzu people, if you aren't aware of the Switch emulator, Yuzu, they commonly came into our like repos and were like, hey, this is broken. Hey, can you add this? Can you fix this? We're like, okay, like sure. I mean, they're using Vulkan, sure. No. Fun fact, emulators, like the Switch emulator, Switch games are mostly CPU bound, not GPU bound. That's why if you run a Switch emulator on like your laptop, it's like faster because it wasn't the GPU that was the problem, it was the CPU. No, emulators love Vulkan because it's like the perfect abstraction level that they can just port it all. And so yeah, it's I don't know what the real question was there anymore, but yeah, it's gonna run on Vulkan, and I will get bug issues. I will just treat it like anybody else, any other open source issue.
So you're admitting that you've worked with those before?
I'm just fixing issues, okay? Like, other people are gonna hit them too. Like, someone reported an issue. Like, I don't know. Maybe they just like looked at code randomly. I don't know.
Emulation is legal, just not emulating copyrighted works.
Have you ever used copyrighted works?
All I'm gonna say is emulators are real good at like pushing boundaries you never heard of the API. So yeah, they're really good at pushing API limits. Any other? You had one?
Yeah, I was just gonna say, how about like reverse engineers? Like, I think not too long ago, like they cracked Apple Silicon.
So for what?
Like the reverse engineers. I think not too long ago they cracked the Apple Silicon.
So okay, so the big thing, Vulkan. There's actually my company actually works on a thing called Cosmic Crisp that just came out, which is Vulkan on metal. So we now have a working. It actually uses. It's really cool. So it actually does. There were people out there who reverse engineered the APIs on metal and the Apple. So then what we do is, again, welcome to layering world. So you run Vulkan. It goes through the Mesa driver. It gets in the Mesa driver. So in the driver, they then switch over and run it on the Apple hardware, so on metal. So we actually have a way of like, because of this effort, we actually have a way that we can just run Vulkan and then layer on top of Mac, so people can like write Vulkan code and it just works on Mac. So that's been a big, newer development of the ecosystem.
How does it differ from like Molten VK?
So Molten VK took the approach above it, which was, let's take the API calls and try to directly translate it, where it went into the driver. I take that kind of like level inside, it gives you a little bit more flexibility, and like the biggest problem with Molten VK is the shaders. Like all things shaders are a topic, deep topic. So the biggest issue is you have to get the shaders out from like Spear V. You have to bring it out to Metal's shading language. Whatever they call it, MLSL. It was really Molten VK never had a good way to do that. Well, because of all that work, the reverse engineering, the Mesa driver literally already had that code. They already had the code. People already had all this code to like. It's really hard to get good compile engineers. So if you could just use open source compile engineers' efforts to like finish that off, that was kind of the missing piece. So that was kind of that was one of the big issues. Was trying to do that at the wrong abstraction level.
So instead of like Vulkan just calling the Metal API, it's like
it's literally Vulkan. It's what you call the Vulkan driver, and the driver is calling the Metal API. It's like an extra level deeper. So they just. I guess I should. My boss would be happy if I talk about this. Yeah, look at that, Lunar G, that's us. Yeah. So Cosmic Crisp, that's our new driver that we just released, I think a month ago. Yeah, so if you're on a Mac, go test it out. I don't know. Report issues, they'll love it. We have 2 guys on it right now. They'll take all your issues. They'll take as much feedback to get this to work. So, yeah. Anybody else? Go.
You mentioned how like they have the user space drivers that'll reach out to the Linux kernel mode driver.
Yeah.
Like what prevents any application from just like making a syscall and reaching out to the kernel and saying, I don't care what X11 or Wayland is doing, just render it to the screen. How does that work from like a security perspective?
I don't think there is a handshake. I mean, well, okay, so the kernel driver, the only thing the kernel driver can do is allocate memory and like synchronize work to the GPU. So I mean, the worst you can do is like black out someone's screen, I guess. I mean, you're not gonna be able to peek at information. I mean, you're gonna like just black out a screen, I guess.
Okay.
So it's like, yeah, no, it's like an Intel, it's just an octal call. I mean, yeah, I guess I could just technically call that octal call. I think there's nothing like worthwhile to go after there. Maybe that's the problem.
I was just wondering, like, does any application have permission to write to the entire screen?
No, because again, like the app is not in charge. The app has to hand it over to, like the app can't. The app has to. The only person in charge of it is like in this case, like my case was like Mutter, right?
Mm-hmm.
You have to hand it to Mutter. You have to hand it to someone. I think positive. So that's the thing. You're just building all the GPU do is just rendering memory in this 2D array. It's up to the positor to put it there.
Mm-hmm.
So the GPU doesn't actually push it to the screen. The part I really don't understand, this is the part that gets below, like out of my league, is like, I obviously put the HDMI, I've never actually figured this out, you put the HDMI cable into your dedicated GPU graphics card. I really don't grasp like how that handshaking all works. That just seems, that's kind of my like black box magic. I'm like, I don't know, somehow they handshake. Good, yeah, thank you. Okay, it is 9. I will stay as late as we want to. If you have a question, I'll stay. But yeah.
Thank you. Thank you.